Hi there. In this video, we're going to talk about consistency of a set of equations and a test for consistency. So what we mean when we say a system of equations should be consistent. We could have, for instance, a set of three linear equations. They are a1x plus b1y plus d1 equal to 0. Then we have a2x plus b2y plus d2 equal to 0, and then a3x plus b3y plus d3 equal to 0. So you can see if we analyze the system of equations, we have three equations and we have two unknowns. So those two unknowns are x and y. So two unknowns. So this presents a bit of an issue because we only need two equations to solve the variables x and y. So if we label these equations 1, 2, and 3, we could solve for x and y just by only considering equation 1 and equation 2. So let's just say we do that and we get values for x and y. If we now take those values and for x and y and we substitute them in equation 3, it doesn't necessarily mean that it's going to obey equation 3. It doesn't mean that the values for x and y that we calculated using these first two equations are going to be valid for the third equation. Similarly, we could solve for x and y using equations 2 and 3. And similarly, we can solve for x and y using equations 1 and 3. So now we need to consider a mechanism by which the values that we get for x and y will be valid for all three equations and not just for the two equations which we used to solve the system. So we need to do some kind of test to check if this is a consistent set of equations. So when we use the word consistent, we mean that any value for x and y that we calculate using any two of these equations will be valid for the remaining equation that we did not use. So to check if this system is consistent, all we need to do is we take the determinant of these coefficients and we set them equal to 0. So we take a1, b1, d1, and then a2, b2, d2, and then a3, b3, and d3. Make a 3 by 3 determinant of this, and we substitute all of these values in, we compute this determinant, and if it's equal to 0, then it means that this is a consistent set of equations, and we can solve for x and y using any two of these equations. So we can do that, and we can illustrate it with a problem, but what is frequently encountered is that we would not specify one of these coefficients. For example, d2 or d3, we would express some of these coefficients in terms of some other variable, and then we would solve for that variable for a number of that variable. So we would find a number associated for that variable, which makes this entire system of equations consistent. So let me illustrate what I mean by just a simple example. So this example that we're considering, we can have in equation 1, 3x plus y plus 2, and then we can have 4x plus 2y minus k. So this k is what we'll be calculating. We'll be finding a value of k that makes the system consistent. And then we have 2 minus y, and then plus 3k. So k is not a variable. It's just a constant. It's just something that we're going to be calculating such that this set of equations is constant. And how do we go about doing that? We find this determinant and then set it equal to 0 and then solve for that value of k. So let's form that determinant. So we have 3, and we have 1, and then we have 2, and then we have 4, 2, and minus k, 4, 2, and minus k. Then we have 2 minus 1 and 3k, 2 minus 1, and then 3k. And what we do is we find this determinant and we set it equal to 0. So that's what we're going to do, and we're going to find the value of k that satisfies this equation. So let's go about doing that. So firstly, we'll take element 3. So that's in the first column and first row. So we have 3, and we multiply by the minor of 3. So just to recap what we do to find the minor, we block this first row and this first column and write what's left and make a determinant of it. So it's going to be 2 minus k, and then minus 1 and 3k, minus, that's the second term. So we have the element 1 multiplied by the minor of 1. We block out first row and second column, so what's left is 4, then minus k, then we have 2 and 3k. And then lastly we have 2, and then we block out first row and third column, and what's left is 4, 2, and 2 minus 1. 4, 2, and 2 and minus 1, and then we set this equal to 0, and now we evaluate each of these terms and solve for k. So we have 3, and then evaluating this 2 by 2 determinant, it's going to be 2 times 3k. Remember that we multiply across diagonally, so it's 2 times 3k, and minus k times minus 1. We have minus k times minus 1. Then we have minus, that's 1 there. Then we have 4 times 3k, 4 times 3k. Then minus k times 2, minus k times 2. And then lastly, we have plus 2 into 4 times minus 1, minus 2 times 2. And this is equal to 0. So now we just go about solving for k. So let's do that. So we have 3 into 2 times 3, which is 6, so that's 6k. Then minus k times minus 1, minus gives us a plus, plus times a minus gives us a minus. So we have minus k. Then we have minus, then 4 times 3, which is 12. 12k, then minus and a minus gives us a plus, so we have plus 2k. And then lastly, plus 2 into minus 4, that's 4 times minus 1, minus 2 times 2, which is minus 4, and this is equal to 0. We can just easily solve this. So we have 6 minus 1, which is just minus k times 3 is minus 15k. Sorry, 15k. Then we have 12 plus 2 is 14, so we have minus 14k. And then we have minus 4 times minus 4, minus 4 minus 4 is minus 16. Minus 8 times 2 is minus 16. That's equal to 0. And then 15 minus 14 is just k. So k is equal to 16. So what we're saying is that for this system of equations, when k is equal to 16, then this particular system of equations will be consistent. We can solve for x and y using any two of these equations, and then we will be able to evaluate the system like that. So thank you very much for watching.